I'm gonna be making a video for the chemistry final. It's gonna be in the same style that Mustafa made the physics final, where I just go over the topics and explain them instead of doing the quizzes. So um, we have chapter 1, 2, 3, 4, and then we have topics. We have topic 6, 9, topic 6, 8, 9, 11. This is about equilibrium. This is about solubility. This is about acids and bases, and this is about the electrolysis electrochemical cell. This is the nitrogen, I think. This is the sulfur. One of these is sulfur, the other is nitrogen. This is halides. It was self-study, but so I'm gonna go over it. And this one is the tests for gases. All of these are just memorization. There is no explaining to them, so I'll just briefly go over them. There isn't that much to explain. Okay, so I'll start with chapter 1, equilibrium. So equilibrium happens in reversible equations. So you have A plus B and then C plus D. Equilibrium, from the outside, it looks like there's nothing happening. When something reaches equilibrium, if you look at it from the outside, it looks like nothing's happening. You just see a beaker. You'll see at first it starts to change color, and then out of nowhere it just stops. What you see from the outside and things you can measure, for example, color, mass, temperature, stuff like that, it's called macroscopic. So you reach equilibrium when your macroscopic properties are constant. It happens at the same rate and at the same time. So let's say we have this. So this is the reactants and this is the product. So we have a beaker with with A's, B's everywhere, yeah? And then we have another beaker with C, D. We mix them. So then A and B, sorry, something like that. So we have A and B. They turn into C and D. So we have A and B turn into C and D. But at the same time, C and D are turning into A and B. So for example, let's say A turns into C. At the same time, C is turning into A. So they come in like a really let's say, right in between A and C. So it's instead of being fully A or being fully C, it's right in between. So that's basically equilibrium. It's two reactions happening at the same time and at the same rate. There is obviously a lot more, but that's the basic outside. It's when two reactions happen at the exact same time, same rate, everything. You can tell it by when the macroscopic properties are constant. Yani when from the outside nothing looks like it's changing. Like for example, let's say this is blue and this is yellow. So it starts off as blue and then it slowly turns into yellow, and then at the same time it's turning into yellow, it's turning back into blue. صح? So instead of being blue or yellow, comes a bit in between, becomes green. So, and then it just stays green. So when you start, it becomes blue, and then you see it slowly become yellower and yellower and yellower until it just becomes green. But macroscopically, which means if you have a microscope and you look into the atoms, it's still changing, still constantly changing. So you have something called, this is really important, Le Chatelier's principle. I'm gonna write it here. Le Chatelier's some French guy. Which is basically if any change happens to the system or equation or whatever. So this counts as a system, yeah? So I'm just gonna call it system from now on instead of reaction or equation. If anything happens, the system itself will try to counteract it. Let's say the pressure is, the system will try to decrease the pressure, and it happens in a lot of different ways. I'll give a few examples. So let's say this process is endothermic, صح? What does that mean? That means that the heat is absorbed. So that means the heat is here, plus heat. I'm gonna rewrite it with everything. So we have A plus B plus heat, C plus D. Let's say the person doing the experiment increases the temperature, صح? So let's say the temperature goes from 10 to 20. What will the system do to go back to 10? مش صح, it's endothermic. That means the heat is used up here. So this is how the system works. You have A and B. You have it's dissolved in something. And then you have the heat in here. A and B take the heat from here and turn into C and D. So if somebody gives more heat, what's it gonna do to turn back? It's gonna take up more heat from the surroundings to decrease. So which way takes heat? This way or this way? It's endothermic, so that means the forward reaction takes heat. Because these two, the way the reaction works is they take heat from the surrounding and then they turn into these. So if somebody increases the heat, the system itself is gonna absorb more heat to decrease the surrounding. So it's gonna take more here. This is gonna be used more, and this is gonna increase. What does that mean? That means when the temperature increases to decrease it, it takes in heat. So it uses this reaction more, which in turn what gives you more of this. So instead of being at perfect equilibrium, it's gonna be less of this and more of this. This is Le Chatelier's principle. And we have also with pressure. So let's say we have 2A plus B, instead of just A, 2A plus B gives and takes C plus D. So let's say somebody increases the total pressure of the whole thing. The way the system, this one you just have to memorize. The way the system decreases the pressure is it goes to the side with less moles. So count all of the total moles. Here you have 2 plus 1. So this is 3 on this side. You have 1 plus 1. I'm gonna erase it because it looks like zeros. So here you have 2 and here you have 1. Here you have 1 and here you have 1. Add up the moles on each side. So here you have 3 moles in total. And here you have 2 moles in total. So that means it's gonna lean to the side with less moles. So it's gonna lean more to the side. This is what you have to know about Le Chatelier's principle. It's always gonna try to even out. Just look at what it's saying and think really hard. Or for example, let's say they increase concentration here. To decrease it, it's gonna go to this side. Again, just this part needs thinking. If, for example, this was 1 instead of 2, so that means it's 2 moles on each side, the equilibrium is not going to change. No matter how much you increase the pressure, it's not going to change because the moles are equal on both sides. So that's one case where it doesn't change. When the number of moles of gaseous products, so N of G, reactants, equals to N of G products. That's one case. The second case is if you add a noble gas. So usually if you add something, it changes the usually when you add a substance, change the equilibrium, because more gas means more pressure, means it means there's gonna be a new reaction, صح? If you add an inert gas, so a noble gas, nothing's gonna change. I'm going in order through all of the notes I took from before. That's almost everything for equilibrium. You have to memorize the Le Chatelier's principle and the definition. The definition is when a reversible reaction happens, when both sides of a reversible reaction happen at the same rate and at the same time. So now there's also, sorry, I forgot about the equilibrium constant. This is something really important, and this is really helpful in chapter 3 also. So we have something called an equilibrium constant, which just shows us, it's like a number for the equilibrium. You know how equal are both sides of the reaction. So the way we do it is, so we use K for the equilibrium constant. So I'll write it closer up here for more space. Equilibrium constant is used as K. And the way we find K is the ratio of the concentration of the products plus the ratio over the ratio of the concentration of the reactant. So it's like this. So this is used for the concentration, صح? Concentration of C times the concentration of D over concentration of A times the concentration of B, and it's to the power of the subscript. So I'll write sub for the subscript. Here you can see all of the subscripts are 0 أصلا. So let's say, for example, it was C2 plus D, then it would be squared like that. Subscript, subscript, subscript. That's the main thing you need to know. Okay, now I can start with the Haber process. It's either topic 6 or topic 8, but I'm pretty sure this one is topic 6, sulfur. So look, I'm just going in order of what we learned. We have something called the contact process. Contact process is how we get H2SO4. It's not that complicated, but there's a lot of steps. So the first one, it's in 3 main steps and 3 main equations. So the first equation or step you have is you have oxygen plus sulfur gives you SO2 gas. So sulfur, you can get it from the deposit. So like for sulfur, you get it from sulfur deposit, and for oxygen, get it fractional distillation from air. In case they ask you where do you get this from, this one from the deposits, this one from the air. If they just ask you where you get them from, you just say deposits, air. And if they ask you how you get the oxygen, it's just fractional distillation. So this is the first step. Or instead of this, so it's either O2 plus S gives you SO2, or metal sulfide, so metal sulfide plus O2 with heat, it's heated up, gives you metal oxide plus SO2. I'll give an example. Let's say the metal here used is sodium. So we have Na2S plus O2 give you with heat, which is the symbol used, would give you Na2O, Na2O, sorry, Na Na2O plus SO2. This is the first step. The second step is usually the step they'll ask you about the most. The second step is after you've gotten SO2, so you have SO2 from last time, صح? You add O2 to it and you get SO3. Check if it's balanced. If it's not, then you need to balance it. Here, let's see, you have 4 O's, you have 3 O's. So you add a 2 here, add a 2 here, 2S, 4 plus 2, 6, 2 times 3, 6. It's balanced. There's conditions for this step. So the first condition is it's at 450 degrees Celsius. This is the first condition. Second condition is, I'm gonna write C for conditions, yeah? So second condition is it's at 2 atmospheres or 20,000 pascals. And then the third step is you use vanadium oxide as a catalyst. Vanadium oxide is what? V2O5 is a catalyst. V2O5 catalyst. These are the 3 conditions for this step. So we explained the first step and the second step. Now there's one last step for this one. After you get SO3, got SO3 from step 2. So now you add SO3 to already, so you're trying to get H2SO4, so the way you do this, you add H2SO4 that you already have plus H2SO4. You get H2SO4 that you already have, which gives you this H2SO7. And then you take the H2S2O7. H2S2O7. You use H2S2O7 plus water, then you get H2SO4. Step number 3. It is possible to work. This equation is possible for it to work. SO3 plus H2O directly to give you H2SO4 is possible. So it is possible, but it's really dangerous because it's exothermic and it's exothermic, صح? So what? It releases heat, and because of that it could cause splashing of the acid here. The acid could splash and it's corrosive. And for this step, the water is the acid's added to the water instead of the water being added to the acid, because we don't want the acid to spill and everything. Also, this is you don't need to know this, but So platinum can be used as a catalyst, but it's too expensive to be used, and it's poisonous to the sulfur feedstock. Yeah, it's platinum. It's expensive and it's not good for like the pure sulfur. And then the sulfur can come from either ores or from deposits by something called the Frash process. You don't need to know how it works. You don't need to know how it works. Just know it's called the Frash process. So I'm gonna write for oxygen for the first step. Yeah, this is for the first step in case they ask you. The third step is the one they ask you the least about. So S can come from either ores or deposits by something called the Frash process. And then O2 comes from the air by fractional distillation. Fractional distillation. Okay, here is how acid rain is produced. So here's how acid rain is produced. So you have SO2 plus H2O gives you H2SO3. This is called sulfurous acid. Sulfurous. This one is sulfuric acid. This is the difference. Also know that this one is weak and this one is strong. So acid rain, so this is the first step, and then the second step is like sulfurous acid plus oxygen gives you H2SO4. You have two options. You either add 2 here or you add the 1/2 here. Both work. This is step 1 and this is step 2 for acid rain. Now I'm gonna explain something called the Haber process. So the contact process was used to get what sulfuric acid, H2SO4. This is called the Haber process. The Haber process is used for ammonia, NH3, and it has so many uses. So this one is just one step, one equation, unlike the last one. So look, N2 plus H2 gives you NH3. How do you balance this one? You add a 3 here and you add a 2 here. Now it's perfectly balanced. So this is called ammonia. This one has really similar conditions. So the conditions for this one to work as the second step for the contact process, the temperature is the same. Temperature is 450 degrees Celsius. Now here's the difference. The pressure is 200 atmospheres. So this one needs way more pressure. Or 200,000 kPa. يعني what? يعني 200,000 kPa. Like the last one, it's 20,000 20k kPa. This one's 200,000. It's more. And then the catalyst used is, so I'm gonna write catalyst, iron. Just iron, or to be specific, finely divided iron. This is the only equation you have to memorize, and these are the conditions you have to memorize. And sorry, it's reversible. This one is reversible. Same with the SO2 plus O2 gives you SO3. This one's also reversible. Both of them are reversible. The second step from the contact process and the Haber process are really similar. Both reversible, they both need 450 degrees Celsius, but they just have different catalysts and pressure. So here is some things they can ask you. So first, okay, here's the first thing they can ask you. First thing, what can nitrogen be used for? And what can it be used for? Here's a few things. Number one, can use it to make HNO3, nitric acid. 2, it's used in some light bulbs. I'm just gonna write some light bulbs. Some light bulbs, not all. Because you know how sometimes they need like filaments for the gas. 3, it makes an inert atmosphere during two things. Inert atmosphere during welding and also food packaging. It makes an inert atmosphere in both. And there's one last one. As a liquid coolant. Can also be used as a liquid coolant. That's what they can ask you. These are the 4 uses for nitrogen. Next, they can also ask you for where you get the materials. Where do you get the raw materials? Where do you get this is the equation again, just let me write it up here. This is the equation you need to know. They can ask you where do you get these raw materials from. So for nitrogen, is the same as oxygen. From the air using fractional distillation. It's a process to because air isn't just one compound, it's a bunch of different gases. So for example, N2, O2, CO2. So fractional distillation is just a way to split all of the gases from air. I'm pretty sure it's used for the condensing, melting, all of those boiling points and stuff like that. It's also how, for example, they split up ethanol and water, but just just distillation or fractional distillation. It just depends on how close their boiling points are. And then hydrogen comes from methane. So all you need to know, methane is CH4. So then H2 comes from methane. It's a really it's a long process. So there's 2 of them. They're never gonna ask you about them. It's better to know them. So CH4 is methane plus 2H2O gives you CO2 plus 4H2. This is the hydrogen. This is the first way. Or there's a second way. I'm gonna show you. I'm gonna write it down now. this is two equations. So first, CH4 plus H2O, and then nickel is used as a catalyst. So I'm just gonna write nickel up here. Gives you CO plus 3H2, and then CO from here plus H2O gives you CO2 plus H2. These are the two ways. They're never gonna ask you about, but it's, I just wrote them down. So this is what they would ask you. What else? Okay, so these are some just like facts. These ones are important. So during the Haber process, the percent of yield is only 98%, 89% of ammonia, sorry. 89% of ammonia is yield. That's it, no more. Even though the conditions give you low yield, it's still a compromise that gives you an acceptable amount. These conditions give you a low yield, صح? So why would we use them? Because it's used as a compromise to produce at an acceptable rate. So we need to use these ones to make it at a good rate. So if, for example, pressure is too low, it's gonna be way slower. Pressure is too high, it's expensive and it's harder to make it a higher temperature. Also, for the pressure, if you make it too high, it's also really expensive and it could explode. It's dangerous. So these ones are good for the yield. Also, the catalyst has absolutely no effect on the yield at all. It just has an effect on the rate, not the yield. So that means whether we use the catalyst or not, we're still gonna get the exact same amount. It's just how fast we get. So from ammonia, we use something called NPK fertilizers. What's NPK? Nitrogen. You have NPK is NPK. Look at the periodic table. What are they? Nitrogen, phosphorus. What is this? Potassium. These are called NPK fertilizers because these are fertilizers with NP and K. So here's a few examples. For N, you have, I'm gonna write the section for each. So we have NPK. So for N, you have ammonium nitrate. This is an example. You have ammonium nitrate or ammonium phosphate. So for example, ammonium is NH4 plus, صح? So either ammonium nitrate, and then nitrate's NO3 minus, so the plus and the minus cancel out, or ammonium phosphate. Phosphate is PO4 3 minus, so 3 NH4. No, sorry, not like that. So you have, it should be like this. I might be wrong. It should be like this. NH4 3 PO4. So it's one of these. For P, you have ammonium phosphate. The last one. Yeah, it is like this. I just checked the cover book. NH4 3 PO4. For K, you have potassium phosphate or potassium nitrate. So you either have K3PO4 or KNO3. Either of these work. Okay, now we'll move on to I'm pretty sure it's chapter 2, electrolytes. So this is, you have, I'm gonna give an example here. So look, you have here, I'm gonna call it substance X. Substance X. If you heat it with ammonium, so if you make it react with NH4 plus, it gives you NH3. And if you make it react with an acid, it gives you salt. What's this? What's substance X? It's a base. Chapter 2 is when we learn what, like, the difference between acids and base, and then chapter 3 we go way more into detail. So a base plus NH4 plus gives you NH3, and the base plus an acid gives you a salt. So look, all bases end with OH. This is something else you need to know. We all know that what a metal plus a non-metal gives us what? An ionic compound. Ionic compound. Now, how this, what does the metal do? It gives electrons, huh? What does this one do? It gains the electrons. It takes the electrons. This one, then this one, this one gains. What is this ionic compound called? It's called electrolyte. Electrolyte. Why? An electrolyte is something that splits up and gives you ions. Instead of gives here, I'm just gonna write loses, because that's usually what they ask, loses. The ionic compounds in electrolyte, because let's say we have Na plus and Cl minus. The Na lost its electrons, so it became plus, and this one became minus. It gives you NaCl. Right now it's stable. There's no charge, it's stable. But if you dissolve it in water, it splits up into 2 ions. A non-metal and the non-metal. So non-metal plus another non-metal gives you what's called covalent compound, covalent bond, whatever you want to call it. This one is just, they both share. They both share their electrons. They're either called covalent compounds or molecular compounds. The thing you should know is this one is not an electrolyte. Molecular compounds are not electrolytes. Why? Because none of them gain their lost electrons. They're just sharing the extrons they have. That's it. None of them gain, none of them lost, none of them anything. The only exceptions for this rule are acids. So I'm gonna write molecular / covalent, not electrolytes, except what? Acids. Just write the equation to make it. If they're not both stable, for example, you have Cl plus Cl gives you Cl2. Both of these are stable. خلاص. But for example, H plus Cl minus gives you HCl. Not stable, not stable. The main definition for electrolyte is something that gives you ions in water. The way to increase solubility, there's a few ways. So the way you can tell something's electrolyte is when you dissolve it, it gives you ions. So the way to increase the solubility for it to dissolve more, either increase the temperature, solubility up when you increase temperature, or increase solvent, or you crush the solid into a powder, or like you grind it into the powder. So basically just increase, right here, increase surface area. So here I'm gonna give you an easier way to see what happens when they dissolve. So we have group 1, 1, 2, 3, 4, 5. We have group 1 until group 8. So group 1 loses an electron. So I'm gonna write loses E minus. Loses just 1. Group 2 loses 2 E minus. Group 3 loses 3. Group 4 share. Because the atom is made like this. Look, you have the atom inside here, and then all of the shells and everything. So on the first one there's 2, let's say whatever, there's gonna be, so like you have the nucleus and the atom. You have 1, you have, this is the outer shell, the valence one. So this is for group 1, this is for group 2, this is for group 3, and this for group 4. So let's say you have 2 group 4s. What's the point of this one losing 1 and this one losing 1? They're still gonna have the same. So they just share, because your goal is to get 8 in your outer shell. Or for hydrogen 2, because it's so like this is how the shells work. In the first one you have 2, then they become 2, 3, 4, 5, 6, 8, and then they keep becoming 8 after that. Only the first one is 2. Hydrogen only has 1 electron either way. Share electron, only share. And then this one gains 1. Gains 1 E minus. Gains 2 E minus. Gains 3 E minus. And this one just doesn't react at all. No reaction. Why? Because it already has 8 in its outer shell. Noble gases are already stable. They never react because they're already stable. Now we move on to solubility. This is so many rules all at once, and oh, this is so annoying. So many rules you have to memorize. I'm just gonna write them all because this one is just memorization. There's no explanation for this, but so I'm just still gonna write it. So you have two types of salts. You have the soluble ones, soluble, and then you have the insoluble ones. What's the difference between something that's soluble and something that's insoluble? This one dissolves in water, or just in anything in general, but usually in water. This one, no dissolve. This one does not dissolve. So how can you tell which ones are soluble and which ones are insoluble? Because usually it does help sometimes, in case they ask you what's the color of the solution, would the color of the solution change? Is there going to be precipitate? What color is it precipitate? This is where the rules come in. We have in total, I think it's only 6 rules. I honestly thought it was 8. It's easy either way. So the first rule is, this is gonna be showing up a lot, yeah? So I'm gonna call it rule number 1. So rule number 1, so ammonium, I'm not gonna write the names, I'm just gonna write the chemical symbols. Ammonium, group 1, so group 1, or I'm doing alkali metals, hydrogen ions, so H plus, acetates, so CH3COO minus, and nitrates, always soluble. Alkali metals are group 1, soluble, yeah. Alkali metals are group 1, so sodium, potassium, lithium, all of that. So this is rule 1, and I'm gonna keep mentioning it. So remember rule 1, ammonium, group 1, hydrogen, acetates and nitrates. It's easy. So then group 2 are the halides. Halides is group 7. So chlorine, bromine, iodine, Cl minus, Br, all of that. So this is rule 2. So halides, soluble, always soluble except with these 3 things. It's just 3. This one's easy. So it's soluble except with, you have silver, which is Ag plus, lead, which is Pb2 plus, and Cu plus. Not Cu2 plus, it's still soluble with Cu2 plus, it's not with Cu plus. So it's soluble except with these. So if, for example, you see AgCl, it's a solid, it's not soluble. For example, PbI2, it's gonna be a solid. And then I'll give you, for example, let's say you see NaCl, it's soluble, it's aqueous. Because from last time, you can use both rules. So group 1 is soluble with anything, and halides are soluble with everything except these 3. That's rule number 2. Rule number 3 is for sulfates. What the hell? So sulfates are soluble with everything. Sulfates, soluble except, this time you have 4 exceptions. Soluble except you have calcium, barium, strontium, and lead. So just remember capacitor. That's how I remember it. For example, if you have CaSO4, it's insoluble. But Na2SO4 is aqueous. So rule number 3. Rule number 4 is sulfides. So S2 minus. This time it's switched. It's insoluble, except with what? So it's soluble with rule 1, because it's always soluble, so I'm just gonna call it rule 1, and group 2. So for example, Na2S. Na is included in rule 1. It's gonna be aqueous. But for example, let's take a metal that's not in group 2. Aluminum. Al2S3 is gonna be solid, because it's neither in group 2 nor in rule 1. Group 2 plus lead. Also lead is soluble with it. Almost anything with 2 plus is soluble, just except for copper and iron. Rule number 5. OH minus, insoluble except with rule 1 and these two, Ba and Sr. That's rule 5. Rule 6. This one is 3. So you have phosphate, so PO4 3 minus, carbonates, CO3 2 minus, and sulfite, not sulfate, sulfite, SO3 2 minus. It's insoluble except we have rule 1, but except for lithium. Lithium is in group 1 and group 1 is in rule 1, so it's insoluble with everything except for group 1. But it's still, like for example, Li2SO3 is gonna be a solid, but Na2SO3 is gonna be aqueous. This is what you have to know. This was rule 6. That's all of the solubility rules. Here's something you need to know. Sulfate, so SO4 and CO3, when they're solids, are always white in color. Chapter 11, it's honestly just all memorization. Like even when we had the periodic, I didn't make a video about it because it was all memorization. Just the tests for the gases. So I'll go over it a bit. So you have the first test is for SO4, what I mean by test for gases is, let's say you have a substance and you want to see, not gases, sorry, test for substances. So let's say you have, you found a random beaker in the lab and you want to see, oh, I wonder what's inside. So these are tests to find what could be inside. So the first is for SO4 2 minus. This one's really easy. Just add BaNO3, and if it forms a precipitate, then there's SO4. Because why? From the last time, barium is insoluble with sulfur. So I'm pretty sure number 2 and number 3 are the same. Number 2 and number 3 are basically the same. So for both of them, so number 2 is for CO3 2 minus, and for 3 is a test for SO3 2 minus. So the first step for both is, I'm gonna write step 1, add an acid, and there's gonna be gases from both of them. So you're gonna see bubbles, صح? You're gonna see bubbles. Now the bubbles for this one could mean CO2, and here it could mean SO2. How do you test for CO2? Add lime water. If it turns milky, there's CO2. Here, blue litmus paper. Blue litmus. If it turns red, there's SO2. And also another way to tell, SO2 has a really choking smell. Then we have number 4, how to test for NO3. This is how to test for the anions, huh? So number 4 is for NO3 minus. How do you test for it? Add aluminum foil or aluminum powder plus NaOH. If you remember from before, when nitrate is heated with a base in the presence of aluminum, what does it give you? It gives you NH3. Now, how can you tell if you have NH3? Add a red litmus this time, and if it turns blue, you have NH3. Because every other gas that comes from an ion is usually is the other way around. It turns blue red, but this is the only one that turns red blue. So here we have how to test for cations, and it's a really long table. This table is extremely annoying. But I'll group them by colors. So you have 2 cases. You have when you add NaOH, and then you have when you add NH3. And you have 2. You have when in drop-wise, I'm gonna write drops, and then in excess, so it's 2 different cases. Drop slash. So for example, let's say I want to test if I have a specific thing. I add this in a drop, in a drop, صح? And then I see what it does. And then to find out even more, I do it in excess. So the first one is NH4. All you need to know is if you make NH4 react with the NaOH, you get ammonia. And we already got how to test for ammonia last time. And it just doesn't react with ammonia. And then here are 3. These 3 are so annoying. You have zinc. I'm gonna write them here. Zinc 2+, calcium 2+, aluminum 3+. What's the problem? Each of them make a white solid, a white precipitate. White precipitate. This is the problem with each of them. But here's why we do both in. So if you just add, for example, a drop of something of NaOH to whatever has zinc or calcium or aluminum, you're gonna see a little white precipitate from the drop. But then what happens when you add an excess? So look, this is how you remember. that for zinc. So look, zinc will redissolve in both. So it's gonna give you white precipitate, and I'm gonna put RD for redissolve, okay? RD for is gonna redissolve in both. Now calcium doesn't even react, no reaction, and does not redissolve. So I'm gonna put RD doesn't redissolve. Now this one, it redissolves in excess NaOH. But the problem is, how are you gonna tell the difference between this one and this one? But it doesn't redissolve. Also forms a white precipitate, but it doesn't redissolve here. So this, in my opinion, is the most annoying one you have to remember, because even I forget it. But look, zinc dissolves in both, calcium doesn't dissolve in any, and aluminum dissolves only in NaOH. So this is already 4 done. We just have a few more to do. And then we also have to do the flame tests from, because it's the same as last year, but there's also a few extra. I'm just gonna write the colors. I don't like topic 11 is easy, just memorization. I don't even know I need to explain it. So look, then we have Cu2 plus copper. How do you tell? It is a blue precipitate. Wait. Blue precipitate in both. So is the catch. It doesn't redissolve here, but it does redissolve here. Okay, we have how many more? 3 more. So for Fe, you have to memorize for both Fe2 plus and Fe3 plus. I'm gonna do them both separate. So look. So for Fe2 plus, what is it? It's like a dirty dark green, like this one. So green, no, not even this one. Yeah, like this one. Green precipitate. So what? Doesn't redissolve in either. Okay, and now we move on to what? Fe3 plus. Fe3 plus, it's red brown. Let's go red here. See, yeah, it's like this color. Red, brown, precipitate, red, brown, precipitate, and what? It also doesn't redissolve in either. Okay, what's the last one? Last one is chromium. Chromium is similar to Fe2 plus, kind of. Like the description we got, the color I have in my table, the names are different. That's not the issue. The issue is that they might not like give you that in the exam. They might just say green. So chromium 3 plus, here's the problem. It's what? It's not just like any green, it's gray green. So like this is gray, so it's like here. Gray, green, precipitate. Gray, green, precipitate. The problem is in the exam they might just tell you green, nothing else, just green. How do you solve this issue? So look, we said what? Iron in both cases doesn't redissolve in either one of them. صح؟ But how do we tell the difference? For example, if they just tell us green precipitate. Chromium redissolves here. It doesn't here. So if it just tells you green that redissolves in NaOH, it's chromium. If it tells you doesn't, then it's Fe2+. So this is the test for all of the cations. There's more tests I'm gonna write. I just need to be sure of all the colors before I do. You have more tests for gases. So if you want to identify gas, you have a lot. So for H2, what do? You get a lit splint. So just like a stick on fire. You get a lit splint in the presence of H2. So let's say I had a reaction, I think this gas is H2. How am I sure? I get a lit splint. What would H2 do to this lit splint? Makes a popping sound, a really squeaky popping sound, and the fire goes out. Popping sound. Now, how do we test for O2? O2, you bring a glowing splint. Have you ever like lit something on fire and it's not like actively on fire, but it's still like glowing? Like for example, charcoal. Bring a glowing splint. And how do you tell that there's how can you tell that there is any how can you tell that there's any O2 if you bring a glowing splint? It's gonna relight it. So I'm just gonna write that. Relight glowing splint. Okay, we have also for CO2, but we already took it last time. I feel like there's no need to write it because I already wrote it last time. You just add lime water to CO2. We took this before and I already wrote it from last time. So for CO2 it's easy. Same for NH3. I wrote it last time. Now here we have a few different gases. So look, we have for Cl2. Cl2 is what سهلة. So here is how we can test for Cl2. So for Cl2, so the way you test for Cl2, I was doing something. So Cl2 can be tested in this way. Bring a litmus paper. Doesn't matter what color, just bring a litmus paper. So litmus paper, let's say a blue one, yeah? So blue turns into red. Then you're gonna say, oh, but what about last time? We also knew that sulfur turns the blue one red. Here's the thing. And the red one becomes bleached. It becomes like really white and weird and, bleached. So this is the order. If you have it blue, it's gonna become red then bleached. And if you have it red, it's just automatically gonna become bleached. That's how you can test for what? Cl2. Here we have a new one for CO2. Because even for so many of them, if you just put blue litmus paper, it's gonna turn red. Again, like for Cl2, for CO2 even, for SO2. For SO2 you have a different way. So you have a substance called potassium permanganate, which is KM KMN. So Mn MnO4. So potassium, manganese, and oxygen. It's called potassium permanganate or potassium manganate 7. So look, how can you, what does this have to do with anything? So potassium permanganate, its usual color is what? Is purple. So potassium permanganate is purple. What does SO2 do to the purple potassium manganate? It decolorizes it. SO2 decolorizes it. Colorizes it. So that's it. That's all you need to know. And for water, there's 2. So now we also have for H2O. So look, for H2O there's 2. Both liquid or water vapor, whichever one. Let's look. So you have the first one, you take anhydrous. So anhydrous just means it has no water. Anhydrous what? Take anhydrous CuSO4. What happens when you add water to this? It goes from white to blue. So that means CuSO4 is a solid, صح? When it doesn't have any water in it, when it's just dry, it's white. But with water, it's blue. The second way is you take anhydrous. I'm just gonna write this COCl2. Cobalt chloride. First one is copper sulfate. This one is cobalt chloride. What happens for this one? It goes from blue to pink. So, yeah, it turns the blue COCl2, which is anhydrous, pink. Okay, what else do we have? Okay, now this is, I'm pretty sure, the beginning of chapter 3. So this is topic 11. Now, I might be wrong, but this might be chapter 3. Okay, look. So you should know that the pH gives you, how you get the pH is negative log 10 concentration of H plus. What's H? Look, when, let's say for example, NaOH reacts with HCl, what happens? It gives you NaCl plus H2O, صح? بس what? H2O can also split into plus H plus and OH minus. Any equation that has either an acid or a base, just any one of them, no, not that. Any soluble equation, any aqueous equation has both of these in it. So pH, it stands for power of hydrogen. Now look, there is a lot of acids that you do need to memorize, but most of them it's already from before. I'm just gonna write the equations. There's nothing else to write, like, to talk about other than that. There's nothing to explain about acids so far. Just look, one arrow means strong, reversible arrow means weak. That's all you need to know. This means weak, this means strong. We have CL. So for these two, it's the two-step dissociation. If you want one step, you could just remove the second H's. If you want one step, this is the one step, look. This one is the one step, where it just automatically gives you like that, and then there's gonna be two. But the two-step is usually more what they ask for. This is the first four. You guys can take a screenshot if you want. The first three are strong, the last one is weak. And the second step of the dissociation for both is weak. The first one is hydrochloric acid, second one is nitric acid, third one is sulfuric acid, fourth one is sulfurous acid. No, I just have a few more. After sulfurous acid, they barely ask you for any of these. This one, number 6, looks like a base because it ends in this. So it doesn't split up into, for example, this. It doesn't split up here, and this is minus and this plus. No, it splits up. It splits up here. This plus and this is minus. And then the last one. Okay, this is almost all of the acids. I have one last one. So this is 8 acids in total. This is all of them. Now I'm gonna start with this is weak, sorry. Same with carbonic acid, it's weak. The H2CO3. This is bases now. Okay, so for bases, this is the first one, right? 1 second. If you're asking where the O comes from here, all of this happens in water. Just when you're doing it, we don't really write water because it's useless. It's like given kind of that. Because if you just leave it, for example, I have NaOH. If I just leave it there, it's not gonna like split up by itself. It splits up in water. So like water is basically just a given. You just have to like kind of know what happens in water. That's where all of, like for example for the ammonia one, that's where the O's come from. Now I need to explain the concept of what KW. K from chapter 1 is what equilibrium constant, which is products over reactants concentration. What's the formula for water? What's the dissociation formula for water? So the dissociation formula for water is H2O becomes H plus OH minus. And the thing about the K is it's only for aqueous and gas. This is liquid and these two are aqueous, صح? And it's reversible, so not all of the water splits up because then these are still dissolved in the remaining water. So what does that mean? It means that the K of water, or KW, is H plus times OH minus over what? Over nothing. Because there literally is nothing for it to be over. صح? Because it's only for aqueous and gas. So this is just an explanation of how we get the formula. This is the actual formula at the bottom here. Now KW at room temperature, I'm gonna write RT is what? 10 to negative 14 molarity. Again, it's all concentration. And then you also need to know that H plus and OH minus usually in just water are equal. And if they're equal, what does that mean? So that means that 10 to negative 14, let's say it's equal, صح? So that means it's this times this, which means it's, for example, 2h or 2o, whatever you want to call it. What does that mean? That means they're both equal to 10 to negative 7. Because do the math, 10 to negative 7 times 10 to negative 7 equals 10 to negative 14. It's like, it's basic math. If you have x and y, and x is equal to y, you can replace one of them. That's it. Also, the pH formula, I already showed it. Now I have to show the indicators. The indicators, it's used later on in titration. This is chapter 3. After this is chapter 4, which is probably gonna take the longest out of all of them. And also topic 9, which was supposed to be self-study. This is just the highlights from last year. I'll still explain it though. I'll explain it like barely, because we took it already last year. So you have, this is how you can tell if you have an acidic or basic solution. You have something called an indicator. What does that mean? It means it helps you indicate if you have acidic or basic. صح? This is just what the word means. So look. Indicators. You have 4. So number 1 is phenolphthalein. Number 2, you have methyl orange. I don't have enough space to write words to show the colors, so I'm just gonna use like the actual colors from here. Number 3, you have thymolphthalein. Number 4, you have litmus. I'm gonna write base here, and then acid here, and because I don't have enough space to write the colors, I'm gonna use the actual colors. So look, also just 1 second. Okay, look, I'll start from the bottom. So in an acidic solution, litmus is red. Thymolphthalein is colorless. No color. In methyl orange, it's red. And in phenolphthalein, no color. Okay. In a base, phenolphthalein is pink. Methyl orange is yellow. Thymolphthalein is blue. And litmus is also blue. I have an easier trick. Whatever is in an acid, it's either red or colorless. Look, see, it's either red or colorless. How can you remember? See this last part, anything that ends in phthalene, I misspelled it. There's no E at the end, awesome. So look, anything that ends in phthalene is what? Colorless in an acid. And then the other two are red. Then here look, B, pink. Here how do you remember? Orange. مش صح I said anything in an acid that doesn't end in phthalene is red. So it's red. So what and red make yellow? What and red make orange? Yellow. And litmus, you just remember it from before. Okay, now we're gonna take oxides. More specifically, which oxides are basic, which oxides are acidic. Look, so oxides, you have 4 types. First type you have is the metal ones. Second type, non-metal. Third type, amphoteric. Fourth type, neutral. So I'll give examples for both, and then after I'll just give the definition instantly. So the metal ones are basic. The non-metal ones are acidic. Amphoteric are metallic ones that act as both a base and an acid. So you have 3 examples. You have lead oxide, aluminum oxide, and zinc oxide. Neutral are non-metal ones that don't act as any. They don't react as either an acid or a base. H2O, N2O, and CO. As for example, NO2 or CO2 are non-metal oxides, صح? So what does that mean? They're acidic. And A2O is a metal, so it's basic. Oh my god. Now, this is gonna be a long list. But it's gonna take some time. So here we have different reactions of acids. So how do acids react? Like, if an acid, for example, reacts with this, what will it give you? What should you expect? So look, first one, if an acid reacts with a metal, acid plus metal, let me write it up here. So if an acid reacts with a metal, you get 2 things. You get a salt plus H2 gas. This is number 1. What's number 2? Acid plus base. This is the most basic one. Gives you Okay, this is, I'm pretty sure, all of the acid reactions. So an acid and a metal just gives you a salt and a hydrogen gas. So you can tell the salt, take the cation from the metal and the anion from the acid. Number 2, number 5, and number 6 are basically the same. Hydroxide is OH minus. So I said anything that ends with OH minus is a base. And then metal oxides, like I said, from the oxides, they're basic. So those are all the same. You don't have to memorize the difference. Just anything base, like anything base related plus an acid just gives you salt and water. And then the other two are exceptions. Oh, sorry, there's more. I forgot them. Okay, all of the others are just based on. All of them are gonna give you a salt. Most of them give you water, and they might give you a third product, and you can just tell from whatever you're acting. So this one, you should remember it from topic 11 from testing gases. Same with this one. Sulfite is SO3 2 minus. For sulfide, if you react something with sulfide, you get salt and something called H2S. H2S is the hydrogen sulfide. It's the only thing you should know about is it smells like rotten eggs. Everything you can just tell, like for example, sulfide gives you H2S, sulfite gives you SO2, ammonium is a weak acid, and now all of the different methods to prepare a salt. So you have 2 for a soluble and 1 for insoluble. So the first way is something called titration. This is how titration works. You have here I forgot what it's called, a burette. Inside the burette is a base. Usually, most of the time, it's not always gonna be like this. Then you have a conical flask, Erlenmeyer beaker, whatever you want to call it. Inside you have an acid. What do? You slowly, over time, are adding little drops of the base. So look, adding little drops of the base into the acid. How do you know when to stop and when you completely neutralize both? With the acid, add an indicator. Remember from before? So as soon as the color changes, so it's different colors in acid and a base. So if you have something that's acidic, which means the acid is more than the base, it's gonna be this color. So if you have something basic where the base is more than the acid, it's gonna be a different color. So as soon as you see the color change, stop. خلاص, you've neutralized it completely, you've prepared your solid. How can you tell the concentration? So the number of moles usually on one side is equal to the other. So let's say N of the base is equal to N of the acid, because they might ask you, oh, how much concentration will you need to neutralize? How much volume will you need to neutralize? Let's say it's NaOH and HCl. So look, it's a 1-to-1 ratio, صح? So that means the N of here is equal to the N of here. Now, مش صح, if you guys remember from last year, volume for concentration is N over V. Another way we can write this is that what? N equals C times V, صح? So that means what? You see the N's here? We can replace both of them with CV. So CV, so C times V on this side is equal to C times V on this side. So the C of acid times the V of the acid is equal to the C of the base times the V of the base. مش صح? That's it. If they want, for example, how much volume of the base do you need to neutralize X volume of the acid, just equate it, خلاص. And now, so this was the first method to prepare soluble salt. Now I'm gonna do the second method to prepare soluble salt. It's called, this one was called titration. Second one is called the excess method. It's just a bunch of steps. I don't even think I need to write. So basically, look. I'll just خلاص mix it easier. So you have here an acid, صح? Only bases act with acids. So what are 3 types of bases we know? 3 types of metallic bases. Metals. 4. Metal. 4 types of metallic bases we know. Metal oxide, metal hydroxide. What was the last one? The last one is what? Let me. This one is. Add any of these plus the acid in excess. This one in excess. It should be in excess compared to the acid. Why? So in the end, you have an excess solid at the bottom, and then you have a soluble salt solution. What do you do then? You filtrate. You do filtration. So filtrate, you get the filtrate here, and then you just crystallize this one at the bottom. So what? So then this solid excess will be here, and then the salt solution from here will what? Will be in the filtrate. And then you just crystallize. Crystallization, where you heat it, you let it evaporate, and then you dry it afterwards. The third method is called what? The third method is called, it's called precipitation. It's really simple. You just take two aqueous solutions and you mix them together and you get the precipitate. That's it. There's nothing else that much that needs to be explained. You take two two aqueous solutions and mix them. And then you just take the solid at the bottom. And that's all of chapter 3. Now chapter 4. Chapter 4 is all about redox and electrochemical cell. So I'm gonna go over electrochemical cell briefly. But the thing I don't like is they don't explain the book what you use it for. So look, in the book, forget in the book. مش صح most of the time. In a battery, for example, how does a battery work? It stores chemical energy, and no one needs to be used. It turns the chemical energy into what? Electrical energy. Same with, for example, your phone battery. It stores it as chemical energy. When you open it, whenever you text someone, you watch a video, whatever, it turns that chemical energy in the battery into electrical energy to be used. So that's the whole point of electrolysis of the electrochemical cell. You're trying to switch chemical energy into electrical energy. Now, how do you do that? Here I'm gonna explain now. So look, you have two beakers. Then you have this thing called an electrode. It's like a rod connected to either a voltmeter or a lamp or whatever. I'm gonna make it a lamp. You just connect it to one of these to make sure it works. Okay, you also have something called a salt bridge. Now I'm gonna explain how everything works. So you see how it's two terminals, two electrodes. One of them, let's make the one on the right, called the anode, and this one is called the cathode. So the anode is negative and the cathode is positive. So look, the anode, what you have to know is that it's negative. It is the negative terminal, but it's at, for example, the positive terminal or whatever. So in a battery, the anode itself is the negative terminal and the cathode is the positive terminal. Now you have here this thing, it's called the salt bridge. So just let me explain. Here at the anode, oxidation happens. Oxidation, the main one, the main definition that's accepted in every exam. There's so many definitions, but they're useless. So the main definition accepted in exams, and the safest one to always write, is oxidation means you lost electrons, means lost E, and reduction means gain E. How do you remember? You remember with this oil rig. Oxidation involves losing, reduction involves gaining. That's all you have to know. So here the oxidation happens, and here the reduction happens. How can you remember? Now here we're gonna learn animals. An ox. Here's a red cat. Reduction red, cathode cat, and anode ox oxidation. I guess this is something stupid, but it helps you memorize. So here's what happens. You put, we'll say for example, this is zinc and this is copper. So usually we put them in their own solutions. So copper sulfate, no. Copper nitrate is usually the safest. So put CuNO3 2 and then ZnNO3 2. What happens? I said oxidation at the zinc, صح? So the way you can tell which one's the anode is by which one's being oxidized. How do you tell which one's being oxidized? The more reactive one. I'll write for you guys the reactivity table in a second. But here's what happens in... So it becomes Zn plus 2 plus 2 E minus, because it lost 2 electrons, صح? So that means this, the metal rod, it was a lot of zinc solid, but then what happened? It started to decrease in mass. Why? Because it's really slowly losing its solid part and becoming ions. So now we have a bunch of zinc plus here, more than usual, and we have E minus. So the E travel from the anode to the cathode. So that means the E go from here, E minus goes on this way, and the current travels in the other way. So I goes opposite to the electrons. So now what? When we know Cu, what? It gains because it's being reduced. So it goes from Cu2 plus, it gains 2 electrons, and it becomes, so just give me red. This shows like how much it lost, and then becomes Cu solid, so that means the Cu2 plus from here, it gains the electrons, and the Cu2 plus here it gains what? It becomes even heavier here. It's basically all you need to know. And the passing of electrons makes the current pass, which then gives us the electricity. The salt bridge, صح, I almost forgot. So salt bridge just has a bunch of ions to reduce the buildup of charge. So the cations here go to here. Why? Because there was a bunch of Cu2 plus here just floating around in the solution, but now they're gone. So the charge went from being neutral, from positive to neutral all of a sudden. So it has to go there to balance. And Mustah here, it's losing a bunch of electrons, and there was already a few zinc pluses, but then because it lost electrons, it became even more. So because it became even more, now how do we balance out the charge? We just send a bunch of anions there. So anions go to the anode, cations go to the cathode. And the salt bridge is what allows the flow of charge, or sorry, the flow of the ions, the reactivity thing. Yeah, just give me a second to draw it. So just remember that while writing it, I'll remind you guys. Just give me a second. I'll write it sideways. In my copybook I have it vertical, but I'll write it sideways so I can have more space. So here is the most reactive. I'm gonna write most, and then here I'm gonna write least. Oh my gosh. What you need to know is the most is copper, the least is, sorry, the most is potassium, the least is copper. It goes down. Group 1 is the most reactive. So K plus Na, then Li. Then you have group 2, Ca 2 plus, Mg 2 plus. Also you need to know that just wait, give me a second. Sorry, copper isn't the weakest. Silver is. So I mixed them up. Copper is the second weakest. So you have the weakest is silver, then copper, then H plus, then lead, Pb2 plus, then iron, then zinc, and then aluminum. It's Al3 plus. I don't have space for the charge, but this is basically the thing. Just know that the most reactive are group 1, and the least reactive are these 3. Everything else will probably be given. The more reactive, that means the one that's gonna get oxidized, which means that it's the one that on the anode. And now I have to explain the oxidation number. So the oxidation number is just something like made up. It's not real. It's just a way for us to tell if something got oxidized or not. So the way something got oxidized, if its oxidation number increased, and if something got reduced, so oxidized equal this, and then reduced equals oxidation number went down. There's 8 rules, and honestly, يعني any element, so just in its elemental state, I'm not really gonna explain them because I still need to explain electrolysis. I'm just gonna write them down. So like any element in its elemental state is zero. خلاص, just forget the paper. Any ion is its charge F minus F in a compound always -1, -1 for oxygen in compounds is -2. So IC just means compound, -2, except O, F2 and peroxides. H2O2, N2O2, stuff like that. Why? صح. F is always -1. What's the total charge here? The total charge here is 0. There's 2. So it's 2 -1 plus, we'll say this one's X equals 0. X is +2. So in OF2 it's +2. And peroxide is gonna make sense now when I explain it. So look, hydrogen, so number 5, H is 1 plus metals with metals, H metal is -1. Number 6 is halides. -1, except with O2 they change. With O2 we don't know what they are, we have to find them. And this last rule is it's honestly kind of stupid, but so like group 1 is +1, group 2 is +2, and aluminum is +3. That's it. Oh, here's even more annoying. Now I have to explain electrolysis. So مش صح electrochemical cell, you're changing electrical chemical to electrical. Electrolysis is the opposite. So the other one happens naturally, this one you have to force it. مش صح I said the more you use an electrode of a metal oh my god. Okay, so here look, the other one you use like a lamp or a voltmeter just to measure. So here you actually use a battery, because here you're trying to force stuff. So look, you have 3 cases. You have 2, and then one of them splits up into 2, so in total it's 3. This one, first one is the molten. So everything inside is liquid. So look, this is what you do. You make, let's say the thing inside is ZnCl2. So you make a table, cation, and then you write the cation this one is gonna get oxidized, this one is gonna get reduced. And by the way, it's the opposite. So last time the anode was negative and the cathode was positive. This time the anode is positive, so the anode is here and the cathode is here. Negative, positive. And you see here now it's in one beaker instead of two, and the electrodes are in it. I'll tell you what they could be in a second. This table is gonna make sense in the next one with the aqueous solutions. Okay, so this one's gonna get reduced, this one's gonna get oxidized. Now we just rewrite it. The reduction half reaction. Reduction involves in gaining, so plus and the cations are gonna go to the cathode and the anions are gonna go to the anode. Remember, anox, red cat. And then this one, so to Cl minus, you have to lose electrons, صح? So مرصاح أصلا it starts off minus, so it gives you 2 electrons and it becomes Cl2. This one is the ox, this one is the oxidation, this one is the reduction. And here I have the second type, is even more annoying because you have to do the tables. I'm not gonna redraw the table from last time. There's another table you need to know that I didn't draw. So let's do ZnCl2 again, but this time in aqueous, not molten, and it splits up into 2 كمان. But we'll just keep it so you have concentrated and you have diluted. I'm gonna start with the concentrated first. So aqueous means dissolved in water. So what does that mean? That there's these ions running around, and there's also H plus and OH minus. The issue is now there's 4 types of ions instead of 2, and there's 2 in each category. How do you know which one's gonna get oxidized? So look, cation, anion. We have Zn2 plus, we have H plus, and then here we have Cl minus, OH minus. Now remember the table from last time, and then I'm also gonna draw the one for the anions. So you have SO4 2 minus, NO3 minus, OH minus, and then we're gonna write halides because the halides are lower. Whichever one is lower is the one that's gonna get oxidized and reduced. So if you remember, H plus was lower than zinc, and then here we can see that OH is higher than the halide, which is Cl. What does that mean? So the lower one's gonna get reduced, so this is the lower one, and the lower one's gonna get oxidized, so is this one. So this is reduction again, this is oxidation, صح? So now they're gonna ask you write the oxidation half reaction at the anode. And we already wrote it last time. 2Cl gives you whatever. And now cation. Cation, they want it. So instead of being zinc 2 plus 2 electrons, no. This time it's gonna be H plus 2 electrons gives you H2 gas. And it gets even more annoying for the diluted. Now I'm gonna explain the diluted. What does diluted mean? Diluted means that there is a lot of water. So here, concentrated means that there was more of this than this, but still the other one was less stable, so whatever. So look, that means there's so much OH minus and there's that much OH minus and there's that much H plus. That's what it means when diluted. That means there's a lot of water. So what does that mean? There's so much that for the anion, it doesn't matter what it is. If you see diluted, automatically OH minus is the one that's gonna be. And by luck this time it was H plus. But for H plus it matters, for OH minus it doesn't. So if you see diluted, that means OH minus is the one that's gonna be reduced, not with the other one. It doesn't matter anymore. As soon as you see the word diluted, just know if they ask oxidation half reaction, it's gonna be for hydroxide, not for whatever it is. Even though chloride is lower, it doesn't matter. But for example, if this was Cu or Ag, let's say it was Ag plus, this one would be the one. Doesn't matter. H for H doesn't matter. Look, let's say instead of Zn, it was Ag. Okay, so now we have Ag and Cl. Ag plus, H plus. If you check the table from last time, Ag was lower, so it's gonna be the one reduced. And here, because it's diluted OH, here's the formula for the OH reduction. OH minus gives you O2 plus 2 H2O plus 4 electrons. Can't write it now, wait, let me just erase everything. But just know that in almost every way possible, electrolysis and electrochemical are opposite. So you have 4 OH minus give you O2 gas plus H2O plus 4 electrons, and put a 2 here to balance. خلاص. Now look, last time I said the electrodes for electrolysis have to be inert. You have 3 options. You have first metal and non-metal. For the metal, you can use platinum or rhodium or rhodium. For the non-metal, you can use graphite, which is just carbon, graphite, both are, it's the same thing. Carbon. It's the same thing, it's the exact same material. So also you have I forgot to mention this for electrochemical and for electrolysis both. You have something called E0, the standard reduction potential, and the standard E0. It's basically just the potential for the energy of whatever. So the way you get it is you have to add them up. Okay, just know you have to add, for example, for electrochemical example, you have, for example, for Ag, the standard Ag is always gonna get reduced, صح? Because it's the lowest from last time. So Ag, the standard reduction is negative 0.8 volts. And for example, let's say for zinc, I think it was, let's say 1.6. How do we get the E0 net? What does net mean? That means you have to add them up. So just add them up. 1.6 plus negative 0.8. You get, this is the standard oxidation. get 0.8. It was a different number, but this is just an example. Let's say they give you both of them negative, or they give you both of them positive. Flip whichever one would make it positive. If you flip this one, it's gonna be negative. But if you flip this one, it's gonna be positive. This is for electrochemical. For electrolysis, you wanna do the opposite. You're gonna ask why. Electrochemical happens by itself, but electrolysis you have to force it. Electrolysis is non-spontaneous. Electrochemical is. No, look. Somebody might say, "Oh, why also do we need electrolysis in the first place?" So look. We have a few reasons to use electrolysis. We're only gonna go into detail for maybe one of two of them. So first one you have is you can use to electrolyze water. What does that mean? Separate water. 2, can use it to collect gases. How? صح, we just saw that if it's diluted you're gonna get O2, and if the metal is really reactive you're gonna get H+. خلاص. Three, produce metals from fused salts of oxides. خلاص. The main one that is really important, forget everything else, all of this isn't important, I'm just giving examples. The main one that we're gonna take is something called electroplating. Electroplating, what does that mean? As in the name, you want to plate something using electrolysis. What does that mean? You want to use electricity to cover something with metal. So why would somebody do this? To make it look better and for it to resist corrosion. Yani for it to stop getting rusted and stuff like that. So here is here's how it's gonna work, look. So at first we have one beaker again, صح? This time we want something. So we want a reactive electrode. So look, we have the positive, which is the cathode, and we have the negative, which is the anode. Put something in here. Look, they're both placed into one beaker. Let's say I have an object, so we're not trying to like just plate something random, we're trying to plate an object. So now I'm gonna draw, for example, like a spoon. So the spoon like this, I'm trying to electroplate this spoon with, let's say this is chromium. What does that mean? That means I need a lot of Cr3 plus in the solution. So we can say that this solution is CrNO3 3. When something gets oxidized, we saw last time. Oh no, I mixed up the anode and the cathode. This one's the anode. When we want to place the object at the cathode, okay? So object should be at the negative. The rod, the metal we want to electroplate the object with should be at the positive. So we said when oxidation happens, that the electrode loses weight and that the cathode, the anode loses the weight. Because why? Because the solid gets turned into ions. The solid we have, the singular solid molecule, splits up into one ion and one electron. But we have a lot of that. We have like way more than just one molecule, yeah? So a bunch of these split up into a bunch of Cr3 plus and 3 electrons. So all of the electrons and all of the Cr3 plus go from here to the spoon, where what happens? Reduction, where they gain these electrons and they gain the Cr. مش صح there's a bunch of Cr3 plus from the solution, and then there's more coming in from here. What else is there? There's a bunch of electrons coming in from here through here. So then what happens? The Cr3 plus from the solution go to the metal and they take the electrons from the outside and then they form onto the object. And that's basically electroplating. Now I have to explain one last thing, which is the halides. The halides, we have 18 groups in the periodic table. Not 18. Look. Yeah, 18. Periodic table is built like this. 1, 2. There's a huge box here. So this one was too big. 2. Just a huge box here. Then it continues like this for 5. We call the 7th one here, group 7, we call them the halides. The halides, they lose 1 electron. There's 1, 2, 3, 4, 5 of them. Or I don't even need the minuses, my bad. They exist in nature diatomically. So look, in nature they're all 2. Stable, they're 2. And reactivity goes down with the group. So that means this one's the most reactive. And this one is the least. This is a gas, and it's yellow-green. Yellow-green. Like this. This one is a liquid, and it's brown. What color would brown be here? It's brown liquid. This one is solid purple, black, sorry. I think it's like, it's not fully black, but it's like, all you need to know is that's solid. When you add something called carbon tetrachloride, which is CCl4, each of them form a different color layer. So Br forms red brown, I forms purple, I forms also brown, and Cl, I think it I need to double check, but both of them, 2 of them form the same color, and the way you can tell the difference. Okay. Fluoride is also pale green gas, and sorry, it's a purple. I is purple as a gas, but black as a solid. And Br is brown red liquid and a brown gas, and acetyl is a black solid. In CCl4, so Br is orange, yeah? In CCl4, this one's orange, and this one is violet purple. That's where I got the purple from, my bad, I mixed it up. And what you need to know is also, they can they're colored precipitates. So look, what I forgot to say last time for the solubility rules, F minus is always soluble. So look, when this makes a precipitate, makes a white precipitate. Let me write in black. White precipitate. Bromide makes Q precipitate. And this one makes a yellow precipitate. And they can displace each other if one is more reactive than the other. I'll show you an example. So look, let's say you have NaBr plus Cl2. Now, which one is more reactive if you look at the thing? Br or Cl? If you look at the thing, Cl is higher, which means it's more reactive. So, because it's more reactive, it displaces it. So it turns into NaCl plus Br 2. No, just balance. But if, for example, instead of Cl it was I, so I'm just gonna then just erase everything at the bottom. It was NaBr plus I2. Br is higher, so it's just no reaction. The highlights also, it's I looked at the file, it's barely a few pages, it's really easy, stuff we took from last year. And yeah, I'm pretty sure that I explained everything. Let me just see if there's anything left. Also, melting point and boiling point go down with the group. خلاص, that's it. If you guys have any questions, you can ask me anytime.